Hello everyone, welcome to week 9 of this live problem solving session for the course Fundamental of Semiconductor Devices with course code E39. Details about me. My name is Mayan Goel and I am a research scholar at the Department of Electrical Engineering, IIT Bombay. And about the course, so it is being taught by Professor Digvijoy Nath, who is an associate professor at ISC Bangalore. And the course plan for this week is the course plan for this week is compound semiconductors. So introduction to compound semiconductors, alloys, commonly used compound semiconductors, heterostructure band diagrams, basics of MOSFET, HEMT, introduction to quantum well, applications of heterostructure device technologies. We are having this tutorial session every Sunday 6 to 8 p.m. and the Google Meet link is the one you are currently joined. So like always, we will do some practice question sessions. So first question, which of the following best defines a compound semiconductor? A, a semiconductor material composed of a single element from group 4 of the periodic table. A semiconductor material composed from two or more different elements, typically from group 3-5 or group 2-4. A material that only exhibits insulating properties at room temperature. A semiconductor that is only used in photovoltaic applications. So, which of the following describes
B, sir. Option B.
that is correct? The answer is a semiconductor material that is made from two or more different elements, and typically one is from group 3, other is from group 5, or one is from group 2, other is from group 6. And if you notice, so why group 3, 5 or group 2, 6? Because if you see the covalency, there the average covalency becomes 4, which is what you get in, which is what you have in silicon. And which of the following is an example of a compound semiconductor? Silicon, germanium, gallium arsenide, graphene.
Gallium arsenide.
That is correct. Gallium arsenide is compound semiconductor. All other three are single elements: silicon, germanium, and carbon. Which of the following is an example of a binary compound semiconductor? Indium gallium arsenide, gallium phosphide, aluminium gallium nitride, aluminium indium phosphide.
Gallium phosphide, sir.
That is correct. So binary compound semiconductor is made up of two elements, whereas a ternary compound semiconductor is made up of three elements. You can also have a quaternary compound semiconductor which is made up of four elements. What type of bonding is found in conventional compound semiconductors like gallium arsenide? Ionic, metallic, covalent, hydrogen.
Covalent, sir.
That is right. The answer is covalent. The primary advantage of compound semiconductors over silicon in high speed applications is higher mobility, lower cost, easier fabrication, and better mechanical strength.
Higher mobility.
That is correct. The answer is higher mobility. So the thing is silicon process silicon silicon electronic processes are fabrication is very well defined that the cost and ease of fabrication is much higher in silicon. I mean, a silicon fabrication is lower cost and much easier to fabricate compared to compound semiconductors. But still, there are some limitations to silicon which are being fulfilled by compound semiconductors. Hence, they are being used. The effective mass of electrons in gallium arsenide is lower than in silicon, higher than in silicon, equal to silicon, zero.
Higher than.
Uh, The correct answer is actually lower than in silicon. So if you remember from previous lectures, the mobility is inversely proportional to your effective mass. So if your effective mass is lower, your mobility will be higher. So that is the reason that mobility in gallium arsenide is much higher than in silicon, because the effective mobility is much lower. Effective mass of electrons is much lower. What is the main limitation of silicon in optoelectronic applications? Low thermal conductivity, low carrier mobility, indirect band gap, high cost.
Indirect band gap, sir.
That is correct. The answer would be indirect band gap.
Sir, can you explain the previous one?
This one,
Actually, sir, you say that gallium arsenide has effective mass of electron is low.
yes,
So, sir, is is effective mass is low, there is conductivity is high, mobility is high, mobility is high. Sorry.
yes.
Okay, okay. Effective mass is low. Okay, okay.
E.
Which of the following is a 3,5 semiconductor? Gallium arsenide, cadmium
Gallium
telluride,
arsenide.
zinc oxide, silicon carbide.
Gallium arsenide, sir.
Gallium arsenide.
That is correct. Gallium arsenide is a 3,5 semiconductor. So zinc is a transition metal. So it comes in type. Zinc is transition metal. Silicon carbide both are 4,4. Cadmium telluride is I think 2,6.
Cadmium iron 26.
I think
And silicon carbide is a 4,4, I think.
yes, because silicon carbon both are 4.
Four, both are 4.
What is
Silicon
the
carbide, silicon carbide is not a means compound semiconductor, na?
It is a compound semiconductor.
Acha, average 4. Average is 4. Okay, okay, sir. Okay.
Uh, What is the primary application of mercury cadmium telluride? Solar cells, high-speed transistors, mid-dia photodetectors, power electronics.
I think that is mid-IR photodetector.
That is correct. So by by changing the amount of mercury and cadmium, you can have a very high mobility, very high band gap tuning in the mid-IR region. Hence, they are used in that purpose. If the, so now a numerical, it's very simple. If a band gap of a material is zero point 0.3 electron volts, what is the longest wavelength it can detect in infrared applications? 1242 nanometer, 3105 nanometer, 4140 nanometer, 6000 nanometer.
4140 nanometer.
That is correct. The answer would be 4140 nanometer. You just have to, lambda equals to hc by e. So hc, you just have to use 1242 ev per nanometer, and you divide it, you get 4140 nanometer, which is your mid IR range. What is Vegard's law related to? The stability of silicon, the relation between alloy composition and band gap, the efficiency of solar cells, the manufacturing process of LEDs.
The relationship between alloy composition and band gap.
That is correct. Vegard's law relates alloy composition and band gap. So questions now related to this. According to Vegard's law, the lattice constant of an alloy AX B1 minus XC is given by A equals to A plus AB, A equals to XAA plus 1 minus XAB, A equals to AX multiplied by AB, A equals to AX plus XAB.
Option B.
Sir, can I move to the previous slide, sir? 1 minute.
Yes.
Okay, sir. Okay, sir.
So the answer to this would be A equals to XAA plus 1 minus XAB.
Sir, can you explain this, sir?
So so you have two compound semiconductors AC and BC, where so your A and B are different, your C is common, and now you are creating an alloy between them. So this X is called mole fraction. So if how many in 1 mole of this compound AXB1 minus XC, how many moles of A will be there? So this total is 1 mole. So obviously the moles are the 1 mole is divided between atoms of A and B. So if A has X number of moles, then B will have 1 minus X number of moles. So that is how this thing comes as AX B1 minus XC. So now the lattice constant, I assume that the lattice constant of AC, the compound semiconductor AC is AA, and the lattice constant of compound semiconductor BC is AB. So now I have to find out the lattice constant of this alloy AX B1 minus XC. So that is given by this formula. A equals to X of the lattice constant of AC plus 1 minus X of lattice constant of BC.
Sir, can you explain once more, sir?
Yeah, so let's say my let's say I am taking zero point 0.3, I am taking 0.5, zero point 0.3 moles of AC. So I have two AC and my another is BC. So if I take 0.3 moles of this and 0.7 moles of this, my final compound will become A of 0.3, B of 0.7, C. Now if the lattice constant of AC is alpha 1 and the lattice constant of AB is alpha 2, so what will be the lattice constant of my this, which is alpha 3? Tell me what will be the lattice constant, how can I find out alpha 3?
A alpha 1 plus B 1 minus alpha 1.
What is your A and B? This is a mathematical equation.
Okay, okay, sir. So, sir, the value of A with 0.3 and B will be 0.7.
Yeah, so this is your X
Yes, 0.3 will be your X.
and this is then your 1 minus X.
1 minus X, obviously, sir. So, X into A lattice constant plus 1 minus X into AB.
Yes.
Sir, how it is possible the option C will be the answer for a particular example? Because you say that actually we learn that any composition will be if we find out that is constant it will be plus. Is there any possibilities that option C will be the answer?
No.
Okay, okay.
So you see, this is lattice constant. What is the unit of lattice constant?
Centimeter.
Centimeter, right? So all three of these are lattice constants, right?
Yes, sir. Yes, sir. So
All
centimeter
three.
square will be result will be centimeter
This will
square.
be centimeter square. So that is
Okay,
not
okay,
possible.
okay, okay.
So in this case, your alpha 3 will be 0.3 alpha 1 plus
Plus 1
0.7, which is your 1
alpha 2.
minus 0.3.
Okay, 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 sir.
So it will be 0.3 alpha 1 plus 0.7 alpha 2.
Okay, sir.
So in an ALX GA 1 minus X AS alloy, if X equals to 0.5, what will the approximate band gap? So you have to assume linear interpolation between gallium arsenide and aluminum arsenide. Gallium arsenide band gap is 1.42 electron volts. Aluminum arsenide band gap is 2.2 electron volts. Option A 1.7 electron volts, 1.81 electron volts, 2 electron volts, 2.2 electron volts.
Sir, in this case, x and 1 minus x are equal because x is 0.5.
Yes.
So, sir, we can calculate the lattice constant.
Here you are calculating band gap, not lattice constant.
Okay, band gap, band gap.
क्या हो गया था 1.81 option B.
Is the answer will be 1.81 electron volts. So the so the here the formula would be Eg equals to 1 minus x Eg gallium arsenide plus x Eg aluminum arsenide, and both x is 0.5, so 1 minus x is also 0.5. So calculate by that and you get 1.81 electron volts. Now,
1 minute, sir, 1 minute, sir. 1 minute, sir. Previous one.
yes,
1 minute, sir. Okay, sir. Okay.
so if gallium arsenide has a lattice constant of 5.65 angstroms and aluminum arsenide has a lattice constant of 5.66 angstroms, what is the lattice constant of aluminum 0.3, gallium 0.7 arsenide? 5.651 angstrom, 5.653 angstrom, 5.657 angstrom, 5.659 angstrom.
Option B 5.653.
That is correct. The answer would be 5.653 angstrom. So
5.657 will come in, sir.
what?
Point C into 5.66 plus point 0.7 into 5.65.
Wait a second. Okay, so the C will be then wait. Yeah, then C will be the answer. 5.657. The answer would be then 5.657.
No, sir, no, sir. I am making mistake, sir. Your calculation is correct, sir. Sir, your calculation is correct, sir. 5.65. So, sir, we can use Vegard law for calculating band gap and lattice constant both.
Yes.
Sir, 1 minute, sir, please. Allow.
That's correct only. 5.653.
1 minute, sir. Okay. Uh, 0.7 into 5.65. 5.65. Okay, sir.
So, what does the Boeing parameter in Vegar's law indicate? The linear relationship between lattice constants, the non-linear behavior of band gaps in alloys, the melting point of compound semiconductors, the electrical resistance of a material.
Option B,
KB both na, sir.
non-linear behavior of the band gap in alloy.
Yes, the correct answer would be the non-linear behavior of band gaps in alloys. So right now we were assuming that it's a linear relation, so we can go from band gap of one material to the band gap of other material linearly, but there is a non-linearity involved, and that non-linearity is given is calculated using the Boeing parameter. So
Sir,
this is only for band gaps. For lattice constant, we are still assuming a linear relationship,
so sir, option A is also correct, na?
but that is not being given by Boeing parameter. No,
Okay, we can derive this from.
I am asking what is Boeing parameter.
Oh, Boeing parameter. Okay. But this is also correct, sir.
This is not a true or false question.
Okay. Sir, if the multiple select answer is there, then this is also correct.
If I am asking a true or false question, then option A is true, that there is a linear relationship between lattice constants.
Okay.
But I am asking what is Boeing parameter.
Okay.
So now, if the band gap of aluminum nitride is 6.1 electron volts, the band gap of gallium nitride is 3.4 electron volts, and the Boeing parameter is 0.7 electron volts, what is the approximate band gap of aluminum 0.5, gallium 0.5 nitride?
Option A, 4.45.
Sir, here we can perform 0.5 into 6.1 plus 0.5 into 3.4.
But you also have Boeing parameter to consider.
Yes, sir. How the concept, sir?
So what would have been the answer without Boeing parameter?
Without going for a 3.05 and 1.7. So it is 4.75.
So if there was no Boeing parameter, the correct answer would have been 4.75 electron volts. But now you have Boeing parameter to consider also. So now what
Yes,
would be
sir.
the answer?
So we can subtract 6.1 minus 0.7 and 3.4 minus 0.7. Then we can average it.
Without going parameter, it should be 4.65, not 4.75.
No, it is 4.75.
Yes, because 3.05 and 1.7. So 4.75. So it's 2.5 and 2.7.
It's 4.65, sir, without going parameter, and with
2.7 and 1.5. Sir, if we use the Boeing parameter, it will be 4.45, sir.
You are wrong. The correct answer is 4.58. So the Boeing parameter, with Boeing parameter, the formula is this. So this is the formula without Boeing parameter, x of EGA plus 1 minus x of EGB. And by, you apply Boeing parameter as minus B x into 1 minus x.
Sir, but in video lecture, sir taught us that the Boeing parameter should be added, not subtracted.
Wait a second. Online, I can see it's subtraction only.
But in sir's video lecture, it is plus.
Then maybe the Boeing parameter he is writing as negative. So next question.
Sir, 1 minute, sir, 1 minute.
Okay.
The correct answer is 4.58. Yes or no?
Yes.
Okay, sir. Okay. Okay.
So what is the term for the process of growing a material on top of another material such that a crystal structure is maintained? Doping, alloying,
Epitaxy.
epitaxy, diffusion.
Epitaxy, sir. Epitaxy.
Epitaxy.
That is correct. The answer would be epitaxy. So doping is basically when you are modifying the crystal structure of a material by incorporating ions or other elements. Alloying is basically you are mixing two materials and then forming a compound crystal of the two materials. Epitaxy is basically you have one layer of material, then on top of that you are growing a different material. And diffusion is basically your atoms are moving through the lattice, that is called diffusion.
Sir, alloying means, sir, one more time, sir.
Alloying is basically you are mixing two materials, like you are mixing aluminum nitride and gallium nitride in like gaseous phase or liquid phase, and then you are crystallizing it, so it is being crystallized as aluminum gallium nitride.
Okay, sir. Okay.
So it is basically a single crystal, single lattice, right? It is a single lattice of aluminum gallium nitride.
Yes, sir.
In epitaxy you have let's say you have aluminum nitride below, and on top of that I have grown gallium nitride. So I have two materials here, aluminum nitride and gallium nitride, two different materials, different lattices. Which epitaxial growth technique offers the highest precision for monolayer deposition? Physical vapor deposition, molecular beam epitaxy, chemical vapor deposition, electroplating.
CVD.
The answer would be molecular beam epitaxy. So in MB you get the highest level of atomic control, even even better than CVD.
Okay, sir.
In heterostructure devices, lattice mismatch can cause increased carrier mobility, decreased band gap, strain and defects, higher thermal conductivity.
The strain and defect, sir.
That is correct. The answer would be strain and defects. So if you are growing one material over another, and so their lattice constants do not match, then you will have some amount of tensile or compressive strain in the materials, which will create defects also. And you can also have defects like there to compensate for those stress, your lattice may create some defects such that it may remove one layer of one line of atoms itself. There are multiple type of defects that can be caused by lattice mismatch. What is the main difference between a homojunction and a heterojunction? Homojunctions have different electron affinities while heterojunctions have the same. Homojunctions have the same material on both sides while heterojunctions have different materials. Homojunctions require a large band gap difference than heterojunctions. Homojunctions do not form depletion regions.
Sir, B, sir.
That is correct. Homojunctions have the same material on both sides while heterojunctions have different materials. So if you are making like if you are doing a p-type silicon and an n-type silicon, so their junction would be called a homojunction because both are silicons. Even though there is a depletion region forming and all that, there's a band gap there. There will be difference in the band alignment and all, but still it's called homojunction because the material is same. Whereas in heterojunction you will have different materials. So like in one side I am growing gallium nitride, other side I am growing aluminum nitride. So that is a heterojunction. The band alignment where both conduction and valence bands of one semiconductor are within those of another is called type 1 straddling, type 2 staggered, type 3 broken gap, type 4 hybrid.
Type 1.
That is correct. The answer will be type 2 straddling. So and so there are three type. So if you are doing a heterojunction, there are three type of band alignments possible. They are called type 1 or straddling, type 2 or staggered, type 3 or broken gap. There is no such thing as type 4. So in type 1, both the conduction and valence band will be of one will be in another. Let me draw. So let's say this is your heterojunction and this is conduction and valence band of one. and then the second material, if it's like this, or it can be like this. So in this case, the conduction and valence band of the second material are inside the conduction and valence band of the first material. And if you consider this dashed line, then the conduction and valence band of the first material is inside the conduction and valence band of the second material. For staggered, you can have like this or like this. So you can see either the conduction band or the valence band is inside the band gap of another material, and the other one is outside. So it's like a step both. And in type 3, you can have like this. So in type 3, you can see there is no band gap overlap. The band gap are completely outside each other. So you can see the valence band here is in the conduction band here, and the conduction band here is in the valence band here. So that is broken gap. There is no band gap overlap. This is type 3.
Sir, can you explain the type 2, sir, one more time?
So in type 2, you see there is partial band gap overlap. So the conduction band 1 and conduction band 2 are here. The valence band 1. So here, if I take this solid line, so you can see the conduction band is of type the second material is inside the band gap of the first material, but the valence band is outside the first material. Whereas in this case, both conduction band and the valence band were in the band gap of the first material. And similarly,
Okay. So
in
in case of type 1, both conduction band and valence band either inside or outside.
yes,
But in case of type 2, any of the either valence band or conduction band inside,
the
and
other
in
one
type
is
3,
outside.
both are outside. In type 3, both are outside.
Yes, type 3 there will be no band gap overlap.
Overlap. Okay, okay.
What is the fundamental reason of quantum well formation in a heterostructure? Lattice mismatch, energy band discontinuity, higher mobility of electrons,
So,
presence of defects.
so high mobility of electron, I think.
Sir, the option B, energy band discontinuity.
Okay.
That is correct. The answer would be energy band discontinuity. So basically, you have like this. Let's say like you have a type 1 band gap. So these are my Fermi levels. So when I am making the heterostructure, my Fermi levels will align. So this will have to go up. So then what will happen is here my Fermi level will be aligned. But what will happen is this thing will go like this. Like this.
Band bending is there.
Yes. So now you can see this part here. The Fermi level is above so you have a very small potential barrier here, and the Fermi level is above this potential barrier. So there are electrons confined in this region. So this is a quantum well here.
One more time explain sir, this quantum well formation.
Yeah, so you see one. So I have two materials with different band. So there is a discontinuity in the band gap here. You can see.
Yes sir.
So when I'm making this junction, I have to align the Fermi levels, right?
Yes sir.
So when I align the Fermi levels, this band will move up. This part will move up to align.
Okay.
But at the interface, it can't move up because interface it is joint. So that creates a band bending.
Okay sir.
Uh, And so this creates a potential well here due to band bending.
Okay sir. Okay.
And my Fermi level you can see is above this potential well.
Yes sir. Yes sir.
It's above the band. It's above outside the band gap, right?
This is sir like sir strong inversion.
This is even beyond strong inversion
Beyond strong inversion. Okay. Okay.
because in strong inversion also your band gap, your Fermi level does not go outside the band gap.
Yes sir. Yes sir.
Here your Fermi level has gone outside the band gap. So
Okay.
because of that there are electrons here now. Because you have
Okay.
electrons below Fermi level, so you will have electrons here below the Fermi level here, but they are confined in this region now.
Yes sir.
Uh, So that is what your quantum well is. What is the primary function of a quantum well in a heterostructure? I just answered this question. Increase the band gap, confine carriers in a potential well, increase thermal conductivity, increase electrical resistance.
Sir confined carrier in a potential well.
That will be correct. Uh, Aluminium 0.25, gallium 0.75, indium 0.13, gallium 0.83, aluminum nitride, indium nitride. Uh, hmm. so for this, Rohit, for this question, you will have to calculate the band gap of each of the. So you are given 5 materials here: aluminum gallium nitride, indium gallium nitride, aluminum nitride, indium nitride, and gallium nitride. So we'll have to compare the band gaps of the 5 materials here. You will have to compare band gap, electron affinity, all those things. The vacuum level is important at heterojunction band gap band diagrams because it determines the absolute energy levels of conduction and valence bands. It defines the depletion region width. It, it directly influences carrier mobility. It prevents band bending. what would be the answer here?
Sir, is this, I think option A is there. I think I have some idea, sir.
The answer would be option A. So, so just knowing the band gap is not enough to calculate the band diagram. You need to know the level of. So I am saying let's say you have one material of band gap one and another material of band gap 2. Can you tell me what will be the band alignment type? Will it be type 1, type 2, type 3? One
Sir, one
material
is
is one
one
material
meter
is
is,
1 electron volts, another is 2 electron volts.
sir, it can be either two or three, sir. It can be depend upon two or three, sir.
It can be all three of them.
All three, all three. Yes, sir, all three.
But how will you determine which one is it?
With the help of vacuum level, sir.
Yes. So the difference between vacuum level and our conduction band is called electron affinity.
Yes, sir. It is depend upon work function.
Yes. So work function and your so so if I am given like this, but I can't just join them. If my electron affinity here is let's say 1.5 and electron affinity here is 2 and this is now 1 and this is my 2. Now can you tell me what will be this thing?
Type 1, sir, type 1.
Are you sure it is type 1?
Sir, no, sir. It can be. Actually, sir, the vacuum level is different. That's why we cannot say that what is the type 1 or type 2.
No,
But
this is just drawing. This is just drawing. You have to
oh,
like I
sir,
have
it is
drawn.
type 1, sir.
Hmm?
Type 1, sir, because two electron volt is inside the one electron volt as per your drawing, sir.
Don't go for what I have drawn. Go for the values. So what is the what thing when I'm drawing band alignment diagram? What thing I put as common?
Okay, okay, okay. You can move the 1.5 to upward. You can balance the Fermi level. Then you have to draw the figure.
So in band alignment diagram, I don't balance my Fermi level. Band alignment
Okay,
diagram is drawn before making my heterojunction.
okay, okay, okay,
Band alignment diagram does not contain the band bending.
okay, okay, okay. Then you cannot decide, sir.
Now you can decide. So in band alignment diagram, you join your vacuum level. So vacuum level is constant. In band alignment diagram, your vacuum level is constant.
Yes, yes.
So from here, I am making 2 electron volts. From here, I am making 1.5 electron volts. So 1.5 will be like this. My 2 will be like this. Then from here, I will be making 1 electron volts. And from here, I will be making my 2 electron volts.
Sir, type 2, sir, type 2.
Yes, this is type 2.
Yes, sir. Yes, sir.
So without electron affinity, you can't say what is the band alignment with just band gap values. If the conduction band offset delta EC is 0.3 electron volts and the valence band offset delta EV is 0.7 electron volts, what is the total band gap difference between two materials? 0.3 electron volts, 0.7 electron volts, 1 electron volt, 1.4 electron volts.
So it is 1 electron volt because delta EC plus delta EB equal to band gap.
Delta EC plus delta EV is not band gap. It is,
Delta EG, sir. Delta E, band offset, sir. Sorry, sir.
yes, you have to calculate total band gap difference. So what will be the answer? So you are given the difference between the conduction band of two materials. You are given the difference between valence band of two materials.
Sir, option C.
The
Option C.
answer would be 1 electron volts. But can there be another answer? Is is this the only answer? 1 electron volts.
It may be 1.4 or zero point 0.7.
How? You have to justify your answer. You can't just guess. Let me give you a hint. The other answer, if possible, is not in the options.
It might be 0.4.
Point 4, sir. Yes, sir. Point 4. I am also expecting point 4.
Yes, the other answer can be 0.4 also, because your delta EG can be delta EC minus delta EV also. It depends
Yes,
on
sir.
the
Yes.
band alignment.
What, sir?
It will depend on the band alignment. In case of
Okay, okay,
type
okay.
in case of type 1, the answer would be, the band gap difference would be 1 electron volts. But in case of type 2 or type 3, the answer would be 0.4 electron volts. In a type 3 heterodunction, what unique characteristic is observed? The conduction band of one material lies below the valence band of the other. The band gap difference is 0. Both conduction and valence bands align perfectly. No band bending occurs.
Sir, band gap difference is 0.
That is not true.
Sir, option A.
As the answer would be, the conduction band of one material lies below the valence band of the other,
Oh, okay, okay, okay.
which I had explained to you a few slides back.
One material, conduction of one material lies below the valence band of other. Yes, yes, sir. Yes, sorry.
A heterojunction is formed between a material of band gap of 2.5 electron volts and another with 1.5 electron volts. What is the conduction? If the conduction band offset delta EC is 0.6 electron volts, what is the valence band offset delta EB? 0.4 electron volts, 1 electron volts, 1.6 electron volts, or 2 electron volts?
So point four.
So there can be
Can you move to
two
the
answers
previous
here.
slide? 1 minute for 1 minute, sir. The previous slide, sir, for 1 minute. Okay.
So there can be two answers here.
It might be 1 or 0.4.
Sir, point 4 or sir, it will be 1.6.
That is
Point 4 or
that is
1.6.
the answer can be 0.4 or 1.6,
Yes, sir. Yes, sir.
depending on whether it's a type 1 or type 2.
Type 2 or type 1.
So for type 1, the answer would be 0.4. For
Point
type
4.
2, the answer would be 1.6. And
Type 1, sir, answer will be 1.6 and type 2 will be 0.4.
no, you see. So this is my 2.5, right? Now
Yes, sir.
my conduction band offset is 0.6. So it can either be above or below, right?
Yes.
If I draw below
It will be type 1.
and then I make another with 1.5. Now my band gap is given as 1.5. So I make a 1.5 here. So this will become type 1. And now if I calculate my valence band offset, that will come out to be 0.4.
Yes, sir. Yes, sir. Yes, sir.
So this is my type 1. And in another case, if it is above, 0.6 is above, and then I draw my band 1.5 below, and now I calculate this thing, then I will get here 1.6. Because so since this is 0.6, now this will then be 0.9. This difference. This difference is 0.9,
Yes, sir. Yes, sir.
and then this difference would obviously be 1.6 then, because 2.5 minus 0.9 is 1.6.
Yes, sir. Okay, sir.
So this is type 2. So you can either have type 1 or type 2. There can't be a type 3 in this case.
Type C is not possible, sir, because 2.5 and 1.5, how can we draw both are outside the 2.5?
You can draw, but the conduction band offset will have to be greater.
Return.
What is the primary difference between an abrupt and a graded heterojunction? Graded heterojunctions have a uniform band gap throughout. Abrupt heterojunctions have a smoother transition in band gap. Graded heterojunctions have a gradual change in material composition, while abrupt heterojunction change instantaneously. Both have the same band gap but band alignment but different doping concentrations.
Option C.
Option C, sir.
That is correct. The answer would be that graded heterojunctions have a gradual change in metal composition, while abrupt heterojunctions change instantaneously. So it's like if I have to go from if I am joining aluminum nitride and gallium nitride, if I just make an aluminum nitride and then directly on it a gallium nitride, that then I will have a huge change in band gap. That is an abrupt heterojunction. But I can go aluminum nitride, then aluminum 0.2, gallium 0.8 nitride, then aluminum 0.4, gallium 0.6 nitride, then aluminum 0.6, gallium 0.4 nitride, aluminum 0.8, gallium 0.2 nitride, and then gallium, or you get the point. So that is a graded heterojunction. So in that case, my band gap won't look like. So in this case, my band gap will look like this. So let's assume for abrupt, but in graded case, my band gap will look like. So the change is not that huge, but it's a slow change, gradual change. That is called graded heterojunction. What is the key feature of a high electron mobility transistor HEMT? It uses an oxide semiconductor interface. It has a 2D electron gas layer for high mobility. It relies on heavy doping in the channel. It does not require a heterojunction.
Option B.
High
Yes,
2G, 2D electron gas, sir. Layer of high mobility.
Option B, sir.
the answer is option B. Rohit, you want to say something?
No, I'm saying that option B is correct.
Okay, okay. What is the approximate electron mobility in a gallium arsenide based MOD FET at room temperature? 500 centimeter square per volt second, 3000 centimeter square per volt second, 8000 centimeter square per volt second, 15,000 centimeter square per volt second.
I think option D, sir. 15,000 centimeter.
Uh, Wait a second. The answer is, I think, C, 8,000 here. By mistake, I have marked 3,000. The answer, I think, is 8,000 here. But in the case of silicon MOSFETs, the mobility is generally 400. Here, the mobility is like 20 times that, 8,000. Why does a MOD FET exhibit?
So if the mobility is high, then the switching is faster, right?
Yes.
Okay.
Why does a MOD FET exhibit depletion mode operation? It requires a positive gate voltage to turn on. It has a naturally conductive channel at zero bias. It does not have a band gap discontinuity. It uses a P-type channel.
B, sir, option B.
That is correct. So the 2D electron gas that is forming, as I had shown you, by default it is the Fermi level is inside the potential barrier. So you already have conductive channel. You already have electrons. You already have electrons at zero bias. So if you want to turn off this channel, you have to give a negative. You have to give a negative bias so that the Fermi level goes below the Fermi level goes below the potential barrier, and your channel is then depleted. There are no free electrons in the channel. So this is depletion mode. Which of the following statements about a 2D electron gas in HEMT is false? It results from conduction band bending at the heterojunction. It has very high electron mobility. It is formed in the doped L-gas region. It forms without thermal excitation.
D, sir.
Option D.
Option D.
The answer is C. It is formed in the doped L-gas region. So, you know in we had studied in PN junctions that if one region is highly doped and other region is lightly doped, then the band bending will be there in the doped region will not have band bending. The lightly doped region will have band bending. So for 2D electron gas to form, you want band bending. So it is formed in the undoped region, not in the doped region. And you need thermal excitation, otherwise how will you have electrons in the conduction band? So you want electrons in the conduction band. That is why thermal excitation is required. And we just said it has very high mobility, and it is formed by band bending. But band bending is done in the undoped region. So it is formed gallium arsenide doped region and undoped gallium arsenide region. Why are HEMTs preferred over MOSFETs for high frequency applications? They have a lower threshold voltage, they have a higher breakdown voltage, they have a higher cutoff frequency due to lower effective mass and higher mobility, they consume more power. That is correct. The answer is they have a higher cutoff mobility due to lower effective mass and higher mobility. So the mobility is higher, therefore the cutoff frequency is also higher. And cutoff frequency means the frequency at which you still have the gain. You can still you can still differentiate between on and off regions. Which of the following is not an advantage of heterojunction bipolar transistors over traditional bipolar junction transistors? Higher current gain, lower base resistance, lower mobility, faster operation.
Lower mobility, sir.
That is correct. The answer is lower mobility. So HBTs have higher mobility. Therefore, this option is the one. In an HBT, why is the emitter made of a wider bandgap material than the base? To reduce the base resistance, to prevent hole injection into the emitter, to increase the base emitter capacitance, to increase phonon scattering.
Hole injection, sir.
That is correct. The answer would be to prevent hole injection into the emitter. So since the emitter has a bigger, wider band gap than the base, so you can have movement from emitter to the base, but you won't have you will have charge carrier movement from emitter to the base, but not movement from base to the emitter. So that will cause a smaller base current. So the base current will be smaller compared to collector current. So it will result in a higher gain. The current gain in an HBT is exponentially dependent on doping concentration, temperature, band gap difference, base width.
The band gap difference, whatever you told.
That is correct. It is dependent on the band gap difference between the emitter and the base. So higher the band gap difference, higher is the it is dependent exponentially. So even a slightly higher band gap difference will result in huge difference in current gain, which is why HBT is preferred over BJT. What is the main advantage of grading the base in an HBT? It reduces carrier scattering. It creates a quasi-electric field to speed up electrons. It prevents the carrier recombination. It increases the depletion width.
The quasi electrons field to spread speed of the electron.
That is correct. So if you if you change if you change the doping in the base gradually, so going from emitter to the collector, you will have a what is you will have a uh, slanted conduction band. So while going from emitter to the collector, the electrons will speed up, and speed due to this speed up, the time the time constant will reduce, and if time constant reduces, your this thing will increase the cutoff frequency. What is the primary reason GaN based HEMTs are preferred over gallium arsenide HEMTs for high power applications? Lower electron mobility, higher breakdown voltage and power density, lower band gap, lower thermal conductivity. And that is correct. The answer is option B, higher breakdown voltage and power density. So in case of high power applications, one of the most important thing is the how much electric field your material can your material can sustain. So at what does breakdown mean? Breakdown means that your material forms defect channels through which you have conduction. you have defect conduction channel. So that that prevents it to, because that at that point it stops becoming a semiconductor, because there are conduction channels it through which current electrons will pass through. If at these channels form at a certain electric field. So for gallium nitride, this electric field threshold is much higher compared to gallium arsenide. So like if I am giving like 5,000 volts, 1000 volt, 1000 volts potential difference, and my electric field will be very high. So gallium arsenide may break down much before that, but gallium nitride can survive that much electric field. Therefore, it is the preferred. So next, what are the three primary binary compounds that form the 3 nitride family? GAN, in INGN, ALGN, GAL, and ALN, IN, GAS, ALAS, INP, SIC, GAN, BN. Anyone else? Yes, the answer would be gallium nitride, aluminum nitride, indium nitride. So NGAN and LGAN, they are ternary compounds, they are not binary. Arsenide and phosphide, they are not nitrides. SiC, both, it's neither 3 nor nitride. And boron nitride is a 3 nitride, but boron nitride is not a semiconductor, it is a dielectric. It is a 3 nitride compound, but it is not a semiconductor. What is the primary reason gallium nitride is used for blue LEDs? It has an indirect band gap, it has a direct band gap at 3.4 electron volts, it has low electron mobility, it has high resistivity.
Direct band gap.
That is correct. It has direct band gap at 3.4 electron volts, which is what you need for blue light approximately. How can gallium nitride be alloyed to achieve green emission? That is approximately 540 nanometers. Mix gallium nitride with aluminum nitride. Use pure aluminum nitride. Add indium nitride to form InGaN. Add doping elements like silicon. What do you think is the answer is? So the answer to this would be add indium nitride to form InGaN. So we studied that aluminum nitride has a much higher band gap around 6 electron volts. So, and gallium nitride has 3.1 electron volts. So if you mix aluminum nitride with gallium nitride, band gap will go even higher, but you want band gap to reduce. And indium nitride has a band gap around 2 electron volts. So if you mix them, you will have band gap which you need around 540 nanometers. What is the primary drawback of using gallium nitride for optoelectronics? High resistivity, difficulty in p-type doping, low carrier concentration, indirect band gap.
Sir, explain this please.
Yeah, so I was writing. So you should check what values, band gap values for aluminum nitride and gallium nitride you are using to solve this question. Because because the values can slightly vary. Like aluminum nitride can be 6.1, some can write 6.4 electron volts. So that is very important, the values that you are using.
Question is what is the primary drawback of using GNA, GANA, GAN
Gallium
for
nitride.
op-
For
gallium nitride for
optoelectronics.
optoelectronics? Sir, I cannot understand this.
So optoelectronics is basically like LEDs, photoreactors, solar cells, where you are combining optics and electronics. That is called optoelectronics. So and so what is the thing that is stopping us from using gallium nitride for optoelectronics? So the answer here is difficulty in p-type doping.
Sir, how, sir?
So gallium nitride is not easy to dope p-type. So for for LEDs and photoreactors, you want to make a diode. That is, you want to join a p-type and an n-type material, right? But p-type doping in gallium nitride is not easy. It's very
Yes,
difficult.
sir. Yes, sir. Understand, sir. Understand, sir.
In a GaN-based LED, how is white light typically generated? Using multiple PN junctions, by applying a high voltage, by coating a blue LED with phosphor, by using quantum dots.
Option B, sir.
The answer here would be option C, by coating a blue LED with phosphor. So, so we just studied that gallium nitride has a band band gap of 3.4 electron volts, which is easy to make a which is what, so you can make a blue LED from that using using different methods, but if by and phosphor is a phosphor is a like material optically active so if you hit if you shine blue light on phosphor, it will glow yellow, and so phosphor glows yellow, and the blue light from behind, they combine to form the white light. The blue light and the blue light from the LED and the yellow light from the phosphor combines to form the white light.
Yes, sir. Yes, sir.
So if you look at a white LED, no, if you take some white LED and you look at the spectrum of it, so this is like lambda and this is like intensity. This is how a spectrometer, you can see the spectrum basically at what wavelength, what is the intensity of light. So you will see something like this. So this is the light from your blue LED. This would be around 400. You will see approximately nearby 400, 410. This will be the light from a blue LED, and this this broad spectrum is coming from your phosphor, and then the combination of both of these is giving you your white light. GaN based transistors are now competing with silicon in which market? Display technology, power and RF electronics, photovoltaics, memory storage.
B, sir. Power and RF electronics.
That is correct. The answer is power and RF electronics. So we just saw that the gallium nitride has a much higher breakdown voltage, so it can sustain much higher power than silicon, and also due to higher mobility, the cutoff frequency is much higher, so it can do much better frequency than silicon. So it is also used in RF electronics. Now a numerical to end the session. And InGaN quantum well LED is designed for 520 nanometer emission. Assuming a linear band gap relation between gallium nitride 3.4 electron volts and indium nitride 0.7 electron volts, what is what approximate indium composition is required? 30%, 40%, 50%, 60%.
Sir, linear band gap relation can be, please write the formula, sir.
What? What
Formula, sir.
formula for what?
Linear band gap relation, sir.
That is the Vegar's law formula.
Okay, sir.
So it's right. It's saying linear band gap, so you don't have to consider Boeing parameter basically.
Answer we and uh, the value will be taken 0.5, 0.5 each.
That is what you have to calculate. The value.
Okay.
That is the answer. That is the answer that you have to calculate.
So indium composition. Okay. Okay. Sir, E is coming 2.39.
What?
Your E EG of coming is 2.39.
Yeah. Now then calculate your x.
Sir, 37% is coming, sir.
What?
37% is coming, sir.
What?
37%.
Okay. So what is the according to options? What should be the answer?
40, sir. Point 4.
That is correct. So first you calculate the band gap required, which is 1240 by 520, approximately 2.38, 2.39, and then you put then you will get 2.38 equals to 1 minus x 3.4 plus x 0.7, and you solve this, you will get around 0.375, 0.38, which is approximately 0.4. So these are the questions I had for today. Thank you for attending.
Thank you, sir.
Thank you. Hello? Hello? Hello?
हेलो
हाँ, बोलिए.
प्रश्न सर